Howdy folks, hey, so you're here to get some tutorial advice for equilibrium stuff, right? So in this video, you guys should notice that 2 Edmodo, I posted a review and a key. I'm just gonna walk us through, do some think aloud. So if you're still struggling with the basics of equilibrium stuff, hopefully before test coming up in the next day or two, you get this squared away, all right? But as it turns out, we have a reaction, right? And in that reaction, we have an initial molarity of 2.330 molar hydrogen gas, 2.307 molar iodine, all right? And in this reaction, when we're at equilibrium, we end up creating a molarity of 4.582 molar hydrogen iodide gas. All right, so on the actual paper itself, I did give you guys the reaction, right? So this would be H2 plus I2 plus heat will yield 2H I, right? So I gave that to you already in its balanced form, all right? Now, as we proceed, right, the heat is not going to be important to us until we talk about the Chatelier's principle, right? A couple other important things about this reaction is notice that we have 1 mole of hydrogen and 1 mole of iodine will combine to form 2 moles of hydrogen iodide. We're just assuming those are all gases. We're going to run the same reaction all the way through this whole review, right? This is just an example. But hopefully it'll help clarify some things for us. So moving forward, it says to write the equilibrium expression for this reaction. All right. So when we're at equilibrium, we should be able to generate a constant. Now, again, the equilibrium constant only works if we keep things like temperature and pressure constant, right? That takes us all the way up to Le Chatelier's principle stuff. But if the temperature is constant and the pressure is constant, okay, then we can use the same equilibrium constant for any reaction at any initial molarity. All right, if I change that temperature, if I change that pressure, that's going to move our equilibrium constant to a different number, and we have to adjust to generate more reactants or more products, etc., etc. Okay, so when I ask you to apply an equilibrium constant to a new reaction, we're going to assume same temperature, same pressure. If I say we change the temperature or change the pressure, we're going to assume the reaction or the equilibrium constant will be different at that point. But that's all stuff that's going to come up later. I just want to clarify that earlier. Okay, so to find my equilibrium constant for this reaction, right, I'm going to take my value, which we would usually as Kc, because generally we're going to deal with equilibrium in terms of the concentration of our reactants and products, all right? But in this case, if I say hydrogen iodide is my product, remember my products go on the top, so it's going to be the molarity of hydrogen iodide, all right? Now we have coefficient of 2, so our coefficients in equilibrium constant expressions become exponents. Boop. Over, right, the molarity of hydrogen gas, right, and there's no coefficient there, so I don't need an exponent, times the molarity of iodine. And again, because there's no coefficient there, no exponents needed. So if I knew the molarity of hydrogen iodide, hydrogen gas, and iodine at equilibrium, if I knew their actual concentrations, I could then calculate my equilibrium constant. Again, assuming constant temperature and constant pressure, I can use that equilibrium constant to predict the molar concentrations under when I have different amounts of reactants. Okay? All right. So moving forward now, so I've taken our reaction and our equilibrium constant expression, right? I've written those up here. They're going to stay up there for the moment. We're going to use this expression a couple times, all right? But in the next part, what we want to do is we're given, right, the molarity of hydrogen iodide, all right? And so for letter B here, we're asked to use a Rice table, to predict the molarity of hydrogen gas and iodine at equilibrium. So in this case, again, what we're going to do here is, because we do know the molarity of our product, hydrogen iodide at equilibrium, right? We can use that information and what we know about our mole ratios, etc., to predict the molarity of our reactants at equilibrium, right? And in this case, we're going to use a Rice table because it just simply helps us to organize the pertinent information, okay? So, the Rice table is an acronym, of course, so R stands for reaction, so I'm just going to rewrite our reaction. H2 plus I2. I'm not going to worry about the heat in this instance. It's going to yield at equilibrium to HI. And again, what we have to remember about this reaction is this means, because these have coefficients of 1, right? 1 mole hydrogen and 1 mole of iodine will yield 2 moles of hydrogen iodide. Okay? There's my reaction. Now, my initial concentration is given to me as well. That is 2.330 molar hydrogen and 2.307 molar iodine. Now, you're not given an initial concentration of hydrogen iodide, but for what we do, we're always going to assume that begins at a molarity of 0. All right? Now, the C in our Rice table stands for change, so there's going to be a certain change in these two numbers as that number increases, right? And, of course, we're going to remember that this number, because we have a coefficient of 2, right, is going to increase twice as much as those decrease by. All right? So, what we're also given in this bit is the molarity of HI at equilibrium. Okay, so I know my equilibrium concentration of hydrogen iodide is 4.582 molarity. All right, now that little piece of information is important to us because I know that to go from there to there, I have to go plus 4.582. Okay, that's a simple calculation. Because 0 plus 4.582 gives 4.582. All right. Now, we have to simply use some logic and what we understand about mole ratios to infer how this change is reflected on this side of the reaction. So again, if my products are going to increase during the reaction, that means I need to see a corresponding decrease in my reactants. All right? And they're going to decrease by an amount times the mole ratio. Okay, so this one up by 4.582 molarity. That means these are going to decrease, but not by 4.582 molarity. Right? They're going to decrease by half as much. So my mole ratio is 1 to 2. So if this goes up by 4.582, these are going to decrease by 2.582. Decrease by 2.291. Try to do that one in my head. Struggle with good things on my paper. All right. So again, this goes up by 4.582. This is going to go down or decrease by 2.291. It's going to decrease because it's a reactant, and it's going to decrease by half as much because it's a 1 to 2 ratio. All right. This is also a 1 to 2 ratio, so this is going to be decreasing by 2.291 as well. And when we do that calculation, I should get 0.039 molarity as a result there, and 0.016 molarity there as a result. Okay? So I use the Rice table to predict the molarity of hydrogen as 0.039 molar, and the molarity of iodine as 0.016 molarity. Okay? Now, with that in mind, right, I should be able to do part C, which is to predict or to calculate my equilibrium constant. And again, this constant would only apply at this temperature and pressure that this reaction carried out. Okay, so whenever I ask you to apply an equilibrium constant to a new situation, we're talking about only changing the concentration, not the temperature, not the pressure. Temperature and pressure will change the equilibrium constant. Concentration will not. One more time. Temperature and pressure will change your equilibrium constant. The concentration will not change the equilibrium constant. Okay, so if I wanted to know my equilibrium constant, I just simply need to take these three values right here, right? These two I calculated, this one I was given, and I plug them in to my equation here, right? So 4.582 would go up here for the molarity of hydrogen iodine, 0.016 and 0.0139 would go in for my iodine and hydrogen. So my Kc should be equal to 4.582 squared over 0.039 times 0.016. All right. Now, when I plug those numbers into my calculator, it's really important that I take this number and square it first, then divide by, I'm going to do this, that whole number. All right. And there's two ways you can do that. You can put parentheses around your multiplication problem, or you can say this squared divided by that, divided by that. Either way, PEMDAS, the order of operations is important. In order to get there correctly, I should get Kc equals 3.4 times 10 to the 4. Boom. Okay. So that's the gist. So that was our intro to equilibrium, right? And this method that we used here, we used a rice table, and we used a rice table when we are also given a value for the molarity of one of our components at equilibrium. Now, sometimes you are not given any of these values. You're given this value, equilibrium constant, and your initial concentration. Now, that would be more typical of what we would see in a laboratory setting, right? So you would have to use your equilibrium constant and a known initial molarity to predict molarities at equilibrium. So that would be more like what would happen in a laboratory setting. Okay? Because typically when we're trying to predict the reaction, we're trying to predict how much product we get, right? If we already know how much product we get, we don't really care about the rest of this unless we're trying to adjust things. All right? So the next part, the review I gave you asks you to do just that. It's going to say, okay, let's assume we're carrying out this reaction at the same temperature and at the same pressure. What would you expect the equilibrium concentrations to be, all right, if we started with a different molarity of hydrogen and iodine, right? So I'm going to pause, write the next problem up here on the board, and this is a long, nasty one, but we'll get to it. Okay, so moving forward now, right? So I wrote up here the value we already calculated for our equilibrium constant, all right, which is 3.4 times 10 to the 4th. Okay, now we're running the same experiment, same temperature and pressure. That has to be true to continue to use that number. If I change my temperature or pressure, I cannot use the same equilibrium constant. Okay, I did, however, change the concentration, but that's okay. I can still use this when I change the concentration, just not if I change temperature and pressure. Now, so we have an equilibrium constant, first of all, 3.4 times 10 to the 4th, which is a big number, right? So right away, we're going to predict that we're going to end up with a lot more product than we do reactant, right? And that takes us back to that lesson we had a while ago. Okay, so big equilibrium constant means we heavily favor the product side. If we had a really small number, so less than 1, we would be favoring this reactant side. And even at equilibrium, as that reaction occurs, we expect to see more reactant than product. But this is a big number, so we're going to make sure that at the end, when we get our equilibrium constant numbers, our equilibrium concentration numbers, we should end up with a lot more product than we do reactant. All right? But in this case, we're starting with a higher concentration of our two reactants. So that's a 6.40 molarity for both of them. And we know, again, we're going to assume that this is going to start at 0 molarity. All right? And what I want to end up being able to do is define my concentration of all three of those at equilibrium. This is different this time because you're not given any of these numbers, right? So we can't just apply our simple mole ratio to find this, all right? So what we're going to do is a little bit more involved algebra to solve for this, right? So again, I can only do this method if I already know my equilibrium constant, which we just calculated, all right? So here's what I'm going to do. I'm going to apply my mole ratio math here. So I know that this is going to change by a certain amount. So we're going to say this is going to go decrease by x, 1x. This will decrease by 1x, and this will increase by 2x. All right? And when we get to this, x is how much our change is in reference to our mole ratio. So this is going to decrease by 1x because I have a coefficient of 1. This will decrease by 1x because I have a coefficient of 1. This will increase by 2x. Now, I also have to account for how much I started with. So in this case, I'm starting with 0, so I don't need to include that here. In this case, I'm starting with 6.40. So this would be 6.40 minus x, because x is just the change. All right? And this one's going to be 6.40 minus x. Okay? So now, what I have is, if I knew what x was, I would know this number. So I'm just going to plug these in to my equilibrium constant expression right here. All right? And this is why our math ends up being a little bit more involved. But in this case, what I'm going to do is I'm going to solve for x. And x will be my change, right? And then I come back and I plug x in to these three equations to get those three question marks right there. All right? And again, you'll see here shortly why this math is so much more involved. All right? But let's get going. All right, so I'm going to write a little bit smallish off to the side. In order to run all this on one board, there's a lot of math happening here, so hopefully this works out for us. But my equilibrium expression right here. So I know Kc is 3.4 times 10 to the 4th. So I'm going to say 3.4 times 10 to the 4th is equal to, that's not going to work. All right, so I'll pause so I can condense this down so I actually have space to write here, okay? But again, right back to where we left off. If I know my equilibrium constant, 3.4 times 10 to the 4th. All right, and I'm going to express my molarity of HI as 2x, because that's what the molarity of HI will be, because I know the 0 plus 2x will be equal to 2x. You just solve for x. I'm going to say 2x, all right? That value needs to be squared in this expression, all right? Divided by 6.40 minus x times 6.40 minus x. Okay, so there's my equilibrium expression with as much information as I know. Right? Now, there's lots of places where that x pops up. That's why we got to use a little bit more involved algebra to solve for x. But we can, right? We can use algebra to solve for x. So first of all, this times this is the same value as that split. So I'm going to rewrite this one more time. So 3.4 times 10 to the 4th equals 2x squared over 6.40 minus x squared, right? That simplifies our expression a little bit. Now, notice that everything on the right side of my expression is squared, all right? Your algebra teacher, I'm sure, has taught you on more than one occasion. When everything on one side is squared, we can simplify our expression by taking the square root of both sides. That takes the square root of that. That takes the square root of that. And I should get, on my right side, 2x over 6.40 minus x equals 184.4. All right, and all my sig fig hawks out there are already getting on my case because I went 184.4 here. What I like to do when I do big, long, drawn-out calculations is I like to wait till the very end to round to a low number of sig figs. Okay, it's just simpler that way, and that way my rounding doesn't get too screwy from from what my calculator would tell me. All right, so yes, this should be written as 180 if that's the only part of the problem I was doing. Okay, but I'm gonna write a few more digits in there so that I get a more accurate reflection of our final number. All right, so that was my thinking. But anyways, so I simplified this expression. Now, I don't like having unknowns in my denominator, right? So what I'm going to do is I'm going to go ahead and multiply both sides by 6.40 minus x, and when I do so, I should get, right, I'm going to continue this over here. All right, if I go 184.4 times 6.40, I'm going to put parentheses around that, so this distributes into both, right? I should get 1180. All right, there's that expression, and then 184.4 times x equals 2x. All right, now our algebra is getting a little bit simpler. I'm going to add 184.4x to both sides, so I'm going to get 1180 equal to, I'm going to add that, so that should be 186.4x. Divide both sides by 186.4, and I should get 6.33 equals x. All right, fancy math, fancy math. Now, what might happen is you start plugging, you find x and you just plug in 6.33 there and there, forgetting that this isn't a change. X is the amount by which our concentration changes. It is not the actual concentration. So remember that. You've done all this work to get this far. I'd really hate to see you just screw it all up at this point. All right, so I'm going to go back up here and I'm going to subtract 6.33. So I'm going to substitute 6.33 in for x. So this would be 6.40 minus 6.33, as would this be. All right, and this would be 2 times 6.33 to get that number. And when I do that, I should get the value of 0.07 molarity, 0.07 molarity, and 12.6 or 12.7 molarity. Okay, that's what that looks like. Now, sometimes, remember, I've made you do this two ways, the fancy math two ways. This way we get a square root of both sides. Sometimes when you do this, you end up having to use your quadratic equation. All right, which I will write on the board for you when you take the test, FYI. Okay, you're going to have to use algebra to figure that out. Now, small disclaimer, I'm going to give you one problem like this, right, where you have to do the more involved algebra. It will not make or break your test, right? So you can still do fine, probably not get an A, but you can still do fine on your test if you get a little bit lost in this process right here, okay? But just a heads up, there's lots of other stuff that I'm expecting you to be able to do, not just the super involved algebra, but I feel like it's a good push, a good application of your algebra skills to do that. All right, now, the rest of the form here, right, deals with reaction quotient and Le Chatelier's principle, right? And I feel like the answer key that I posted for you guys covers that material sufficiently. All right, because we have an extra long period when you guys are taking this test, I will be able to clarify or clear up some last minute questions when you arrive, but that's it. All right, good luck, keep after it, come talk to me if you need some help.